Hello and welcome to this presentation with the title Use of Generalized Subset Designs, GSD, in Multivariate Calibration. My name is Lennart Eriksson and I'm part of the Sartorius Stadium Data Analytics team. And we provide a series of software solutions that are part of the so-called geometric suite of data analytics solutions. This suite of solutions contains MODDE, Easy Analytics, SIMCA Online, Control Advisor, and Active Dashboard. And there is a whole series of webinars exclusively walking through the different software elements making up the geometric suite. Today we're going to look into one of the new additions in the MODDE 12 software, which is called Generalized Subset Design. MODDE is our design of experiment software, and you can also carry out quality by design, robust optimization, and design space estimation using this software. Here we have a little outline of today's presentation. We will have an introductory part, and since some of you that are perhaps watching or listening to this recording or the live session might not be aware of what multivariate calibration is, I will start by very briefly introducing the concept of multivariate calibration and some notions that are used frequently in this context. We will dwell on a moment on the need for DOE in multivariate calibration and also start to get familiar with the GSD for subset selection. This brings us up to the main application, which deals with determination of water content in tablets. We will have a full account of the application, the background. We will walk through all the stages relating to setting up factors and responses, use the generalized subset design entry in the MODDE software to accomplish the final DOE, and we will also have the data analysis and model interpretation stages being reviewed. Part of this webinar is a demonstration of the GSD functionality inside the MODDE software, and when we are doing that demonstration, we're going to assume some basic level of familiarity with the MODDE software solution. Towards the end, there will also be some concluding remarks. But we will start with a little introduction into what multivariate calibration is. So in brief, in short, you can say that multivariate calibration involves predicting sample properties Y from sample measurement characteristics. Another way to put it is that what you want to accomplish is a situation in which you can use easy to get hold of data to predict more difficult to get hold of data. And usually the easy to get hold of data are often spectral data, spectral measurements. So after spectroscopic measurements of the samples with known qualities or concentrations have been compiled, you're calculating a regression model between the spectral data as the X block and the sample qualities or concentrations or other properties as the Y data. And then in the next step, the idea is to make use of this regression model, and you are then measuring equivalent spectral data for additional samples. You can call them unknown, and you are then inserting these additional spectral data into the regression model and calculate predictions of the Y data for these fresh samples. A very common objective of multivariate calibration is to replace a target or reference method with an alternative measurement technique, which is often spectroscopic in nature. And preferably, this alternative measurement technique should be fast, precise, and ideally also non-destructive to the analyzed samples. One important component in establishing a regression model, a calibration model, is the regression step. And I would like to draw your attention to the OPLS model for multivariate calibration modeling. OPLS is implemented in one of the other software elements, software solutions inside the geometric suite, the SIMCA software solution for multivariate data analysis. So with the OPLS tool, we can concatenate data making up the X block and the Y block with the aim of predicting Y data from X data for the new samples. And at the end, you will then get some sort of quality or concentration or level or proportion or something else. When you're planning for a multivariate calibration application, DOE can come in very, very handy, because one of the prerequisites for accomplishing a successful multivariate calibration model is that the calibration set should contain representative and diverse samples. So it means that this set of samples that you use to train the model should include all variations in both X and Y that are relevant to the problem and which are expected to vary also perhaps over time. So the calibration set must also span in a balanced way the range of the analyte concentrations and also the corresponding concentration ranges of occurring interference. One way of accomplishing such systematic and balanced changes to the composition of the calibration set is to plan everything according to DOE. And if you follow the literature recommendations, when DOE is used to determine the composition of reference samples, at least 5 concentration settings are needed for each analyte, but there are also recommendations going as high as 7 and 9 levels. So when you're using DOE, a fractional factorial design or something else, to plan or induce systematic changes in the concentrations or levels or proportions of the sample constituents, then each such design variable will at the end become a Y variable. It will correspond to one separate Y variable in the multivariate calibration modeling. Another perspective in which DOE can also come into play is when there is a need to make the calibration model more robust to, for instance, batch-to-batch variation in the main constituents. And here you can also impose such simultaneous changes to the concentrations of the constituents and the settings of occurring process and mixture factors using DOE protocols. So when you are using DOE, you should be aware that you can use DOE to influence the composition both of the X block and the Y block for the training set. As you can see on this slide, there are often 3 different data sets used when developing and validating a multivariate calibration model. First of all, we have, of course, the training set, which is also known as the calibration set. And for this set of samples, both the X and the Y are known. And that means you can also estimate model qualities using the familiar statistics, root mean square error of estimation and root mean square error of cross-validation. To test out the relevance of the model in the primary step, you're then often having a second set of data, which we may call the test set, where preferably also the Y data are known, but these samples have not been used to influence the shape of the multivariate calibration model. So in this test step, you will verify the predictive relevance of the model by comparing the measured data with the predictions, and you can quantify how good the model is at predicting the Y using a similar statistics to those up here, but in the prediction stage it is usually known as the root mean square error of prediction. And when the predictive power is satisfactory, the calibration model is then applied to even more new samples, making up the prediction set, which is usually open-ended and growing with time. And it is in this stage you are then measuring the easy to get hold of data, the X data, which are often spectral in nature, inserted into the model and get out predictions of the Y data, the difficult to get hold of data. Very often when you're using DOE in multivariate calibration, there are a number of factors that have many settings, and that means that the number of combinations very quickly can explode and become incomprehensible. So because applications of DOE in multivariate calibration easily involve many factors and many levels, this novel GSD entry in the MODDE software represents a viable and interesting alternative for reducing the number of experiments that are required, but still providing results that are reliable and have a faithful interpretation. And I want to stop for a while by emphasizing what we mean by the term a faithful interpretation. We mean that the regression model and the profile of the regression coefficients that we are calculating based on a reduced set of experimental combinations will be similar and representative for any model that you would be able to calculate using the full set of combinations or the full set of experimental runs. So faithful here means that we are not getting different results if we are running a reduced set of experiments as opposed to running all possible combinations. So below we will review an application of GSD in multivariate calibration. It is a feasibility study investigating the usefulness of microwave resonance spectroscopy for determining water content in tablets. But before we start to walk through the different stages of the application, just 2 more slides to review the basic principle of the GSD approach. In order to illustrate this basic principle of the GSD approach, we will just very quickly look at an application where we have 3 factors. The first factor is a quantitative one. We have the tablet strength in 2 settings, 10 and 40 milligram. The second factor is a qualitative one. It has 3 discrete settings, batch A, batch B, and batch C. And the third factor is the container size of the packaging. It has 3, 30, 100, and 1000 tablets as the settings. Now, if we start to make all combinations here, we see that the total number of combinations would be 24. And with the GSD approach, you can try to fractionate this number of 24 into smaller and complementary subsets. So we can, using the GSD, develop so-called design sets that are complementary, and we are exemplifying the possibility to divide the 24 runs into 3 design sets that are complementary and having 8 runs each. So the first alternative design set would be this one, the second would be this one, and the third would be this one. And the interesting thing is that if you're running all the 3 subsets, they are fully complementary, meaning that once all of the 3 design sets have been investigated and completed, we will have covered all 24 combinations. The interesting thing the interesting aspect with the GSD approach is that each design set may be run in a sequence, or you can also select one specific subset and run it in a standalone mode. And we will discuss more about these possibilities during the discussion of the application and also during the demonstration in the MODDE software. So we will now go into the second stage of this presentation that deals with this application of determining water content in tablets. First of all, we are going to acknowledge the original literature reference. The example dataset is taken from a master's thesis with the title Microwave Spectroscopy, Matrix Effects and Interferences for Water Determinations in Pharmaceutical Formulations. It is written by Haldis Thorodsen about 2 years ago and presented at Chalmers Technical University in Gothenburg in Sweden. And part of the work was also done by researchers coming out of the AstraZeneca facility in the Gothenburg area. The objective of the investigation was to explore methods for determination of water in tablets, and the reference method was the classical Karl-Fischer titration method, and the alternative method was one based on microwave spectroscopy. And I'm going to refer to this original literature source for full details on how the microwave spectroscopy was set up and evaluated. In order to accomplish systematic changes and test out the robustness of the multivariate calibration study, there were 5 factors used to induce systematic changes to the API and some surrounding matrix conditions. The first factor was the type of drug substance. This is a qualitative factor. It had 2 settings, paracetamol and propranolol. The second factor was the particle size of the filler. This is a multi-level factor in 3 settings, 57 micrometer, 115 micrometer, and 228 micrometer. The third factor was the tablet size, small or large tablets expressed in cubic millimeter, with the low setting of 150 and the high setting of 235 cubic millimeters. The fourth factor is a multi-level factor with 3 settings. It relates to tablet hardness, but it is encoded or represented as tensile strength. with a low, medium, and high tensile strength corresponding to 1, 2, and 3 megapascal respectively. And finally, the last factor is one again of a multi-level nature. It has 4 settings. Moisture level is represented as 4 different chambers for conditioning the tablets, and the climates then correspond to different level of humidities expressed as 5, 10, 55, and 75% humidity. In the next stage in the DOE investigation, the researchers defined the responses. And in order to be able to compare the outcome of the reference method with the outcome of the alternative method, 2 responses were specified. And the first response was the water content as determined using the reference method, the Carl-Fisher method. And the second response was the microwave signal of water using the alternative measurement technique. Here we see a screenshot from the MODDE 12 software relating to the dialog where you're specifying the detail of the generalized subset design. So as you will see when we are demonstrating this application inside MODDE software, the first steps are always the same. So inside the design wizard, you will be defining factors and responses in the usual way. And then when you arrive at where you're going to define which subset designs to use, you come to this view. We shall remember that the total number of combinations of the factors is 144 because the factors had 2, 3, 2, 3, and 4 settings respectively. And GSD was here used to define 4 design sets of 36 runs, 4 quarter fractions you can say. And as I told you before, these quarter fractions can be run in a sequence or in a standalone mode. In the software demonstration, I will come back and give more details related to these different reductions and how to interpret them. For the moment, it is enough to say that it was the first quarter fraction that was run in reality. It has 36 experiments. And to these 36 experiments, the investigators decided to add 12 replicated experiments. This is on the high side, maybe 3 to 4 replicates would have been enough, but since it was a feasibility study and the researchers wanted to exploit the properties not only of the GSD but also they were unsure about the replication error, they decided to make 12 replicated experiments. So in total the final design had 48 experiments, 36 coming from the first quarter fraction plus 12 replicates. We are now moving over to analyzing the data, and one important stage in the data analysis is to evaluate the properties of the raw data. And there are several tools available inside the MODDE software for accomplishing a raw data evaluation. And in this particular case, we're looking at the correlation matrix. So the correlation matrix shows that all factors but moisture level are completely uncorrelated with each other. Moisture level is only mildly correlated with the other factors, and it is very close to 0 over here. The condition number for this experimental design is very, very good, so it points to a very good experimental design. And if you recall from other training materials and also recorded webinars, the recommendation is that the condition number for good screening designs should be in the range of 1 to 3. So we have obtained definitely a very, very good design. Another thing that is noteworthy is the high correlation between the 2 responses. The correlation coefficient between the 2 responses is as high as 0.97, suggesting that they are very, very similarly depending on the different factors in the DOE protocol. And the fact that the 2 responses are highly correlated is also evidenced if you make a scatter plot. The scatter plot here is based on plotting the water content as obtained from Carl-Fisher against the microwave response. We can see that the data are grouped, but that comes from one of the underlying factors. It is the moisture level. And there is no other tendency for tailing or skew distribution of the data, so we can analyze them as they are. And we can see that if you're running a regression line between the 2 responses, the R square is 0.949. where I'm pointing. And if you take the square root of this r square, you will get the r that is 0.97 and is displayed in the correlation matrix, just so that we have these two notations connected. Another very, very popular and important and useful plot in the raw data analysis stage is the replicate plot. And the replicate plot shows the numerical spread among the replicated trials in relation to the spread across all experiments in the experimental plan. And in this case, we have very, very good data. The replication errors are much smaller than the variability in the Y data across all experiments. And this is the desirable situation and suggests that we have high quality measurements to work with. We then move over to the model building stage, and here we often look at the plot called the summary of fit plot. The summary of fit plot will always have a quartet of model performance and data performance statistics per response variable. So because we have two responses, we will get two quartets of bars. How to interpret these bars is detailed in other recorded webinars and our training materials, so I will not dwell on that too much. But the important thing is that the performance statistics R square and Q square are high, and that is very, very encouraging. What is a bit unwanted or undesired or unexpected is that we have low values for the yellow bars, the model validity. But in this case, this arises from the very, very small replicate errors and the very large number of degrees of freedom associated with the replicates. So knowing how the model validity is calculated, we arrive at the conclusion that this is more a cosmetic thing rather than a real model problem. So the main conclusion is that we have very, very good models and reliable models to work with. Here we see the regression coefficients, and we can see very, very rapidly that in both situations the moisture level is the most important factor by far, and this is according to expectation, since different tablet conditioning climates was used to deliberately induce systematic changes in the water content in the tablets. Apart from that, the influence of the other factors in the DOE protocol is close to zero, and because the confidence intervals are covering or encompassing the value zero, using the language of a statistician, we can conclude that these terms are not statistically significant. And this relates to both responses. And because of the similarity of the regression coefficient profiles, we can conclude that we have a very robust system and that it is possible to replace the conventional method for measuring moisture in tablets or water content in tablets by the alternative spectroscopy-based method. That is the main conclusion. This brings us to the stage where we will now leave PowerPoint for a while and go over to the MODDE software and conduct a little demo of this use case. And I emphasize that the demo will be concentrating on how to setting up the experimental protocol, giving a detailed walkthrough of the dialog and windows where you're specifying the properties and settings applicable to the generalized subset design. We will not so much discuss the data analysis stage because that we have covered in other presentations. We are now looking at MODDE 12, which has been on the market for about 3 or 4 weeks, or maybe even a month. And there are a couple of new entries under the new thing. And the generalized subset design is the new entry we're focusing on in this presentation. It is a design that generates a sequence of complementary design sets that are interesting and relevant for a number of different types of applications. And as I told you, they can be run in a sequence or in a standalone format. Once we have selected that entry, the design wizard has exactly the same appearance as for any normal DOE. So we define factors in the regular way. So the first factor is the API. It is a qualitative factor and it has the settings paracetamol and propranolol. The second factor is the particle size of the filler. We call it the filler. This is a multi-level factor, quantitative multi-level in micrometer, and the size of the particles was 57, 115 and 228 micrometers. The third factor is a quantitative one. It's the size of the tablet size, and that is measured in cubic millimeters. It has the low setting of 150 and the high setting of 235 cubic millimeters. Factor 4 is the hardness, actually represented as the tensile strength, which is defined in megapascal, and it has 3 settings, so it is a multi-level factor in the settings 1 and 2 and 3. And the last factor, that is the moisture level. It is measured in percentage, and it's also a multi-level, and it has 4 settings: 5%, 10%, 55% and 75%. These are the 5 factors, and the implementation is exactly as for any normal DOE inside the MODDE software. We then click the design wizard, proceed over to the stage where we define the responses, and the first response was KF water content. And it was measured in percent, and the second one was the microwave response, something like that. We click next, and now comes what is different, and you can see that in the define generalized subset designs window, a couple of reductions are already predefined, and these are the first reductions, where reduction A is the full set of 144 runs. You can see here that it says 144 runs. The design condition number for the linear model is 1.22 using the linear model and all combinations. The first reduction, which is called reduction B, means that the 144 runs are divided in 2 half fractions, each comprising 72 runs, and we see then statistics here, the condition number. The third reduction is an alternative where the 144 runs is divided in 3 one-third fractions of 48 runs each, and we can see how they are very similar, but they differ a little in terms of the condition number. All these designs are balanced. Balancing means that inside each design set, all factors are all the levels of all the factors are tested or represented using the same number of runs. If you have an unbalanced situation, it means that in one subset, one factor is tested, the levels of one factor is tested using different number of runs, and that can then change from one design set to another. I'm now going to exemplify how you can add additional reductions, and you can see here that for this particular application, given that it has rather many runs, up to 20 reductions are already prepared, but they aren't invoked in the design set list here. And whenever there is a little star or asterisk, it means that level of reduction will result in design subsets that are balanced, which is a desirable property. So if I take the design reduction 4, it will have 4 quarter fractions, each consisting of 36 runs. And in this case, it is possible to work with that design set,
and we will then decide which design set to operate with by changing up here. If I say A1, the final design, if I click finish, will be the full factorial design in 144 runs. But we will now go for the D reduction degree, the fourth reduction, where we have the design sets D1, D2, D3, and D4. And here you can see which the different design, the properties of these different designs. And the total number of runs is 36. We can say that we want to run one particular with a certain number of replicated points, let's say 3 replicates. In the real application, they used 12 replicated points, but 3 or 4 is perhaps a more realistic option. We can then click finish, and we will see the full DOE where the different design sets are now indicated using a new column called design set. So we can say, compared with the conventional DOE in MODDE, the worksheet now has a few more let's say elements associated with it. One element is what we call the combination ID, indicating which combination of factors is used. The experimental name is a composite thing of the combination ID and which design set that run belong to. Now, if we only want to work with the first subset, which they did in this case, we have a possibility to sort the experiments and so to say highlight the experiments that we want to perform and see all the other experiments, all the other members of the other design sets on a shaded background. So here we have a generalized subset design that is very similar to the one that was used in reality. The difference is that I am using only 4 center points, and it is this, or not center point, I'm using 4 replicates, I should say, and it is that point 31 that is currently replicated. If I want this to be changed, I can always go back into the design wizard and redo this. So here we see how the generalized subset design is configured to be run in a standalone mode, which is possible just by using this little list box where you select which design subsets to work with. So here you have the DOE. You can give it to the technicians or whomever will do the experiments, perform the experiments, enter the data, and carry out the full data analysis as I told you.
So with this introduction to the GSD approach in MODDE 12 in mind and the demonstration of how to set up this design, we now come back to the PowerPoint part for a couple of rounding off remarks. So the main conclusion from this study is that the alternative method for measuring water content in tablets, the microwave spectroscopy-based method, can be used to replace the traditional method being based on Karl-Fischer titration. An important insight is that both methods have not detected any significant effect of the interfering factors, which strongly points to a very robust calibration model, a robust calibration situation. From a more methodological point of view, or a DOE point of view, we have also been able to conclude that the novel GSD approach works very well in the context of multivariate calibration, and the reduced design gave reliable results with lower time consumption and cost of analysis as compared to the full factorial design in 144 runs. And with those words and those concluding remarks, I would like to thank you all for your time and attention. I hope you find this presentation useful and that you will sometime in the future have the possibility to try out the very, very nice properties of the novel GSD approach inside the MODDE 12 software. So, thank you for your time and attention. Goodbye.